My name is Scott McPeak. I'm here to talk about some work that I've done as a grad student at UC Berkeley. I have since graduated about 7 months ago and have started work at Coverity. The work I'll be presenting is joint work with my advisor, George Necula, John Kodemal, Rob Johnson, and Jeff Foster, who are grad students at the same time I was. Jeff is now at Maryland. Rob Johnson is Stony Brook. John Kodemal is going to start at Coverity in a few months as well. Daniel and George are still at Berkeley. Okay. So the theme sort of to this talk is about extensible program analysis, finding ways to write analysis that then let the end users customize these to provide rules and language constructs specific to the things that they're trying to check. And so we want to have a parser that allows language extensions, an internal language infrastructure, which additional like type checking rules and so forth can be added, and then ultimately a program analysis framework that allows program specific idiom recognition and checking of specific properties in the domain. So the start of this, there's sort of three parts of this: the parser, the parser generator, the parser, and the analysis. So the first part is a parser generator. This is called Elkhound. It's a tool that generates parsers that use the GLR, which is a Generalized LR parsing algorithm. This is an extension of LALR1 in which you can give it a grammar, essentially any context-free grammar, and it will generate a parser for that language. It does not have to be LALR1. So this has two main advantages. First, it allows unbounded look ahead. So it doesn't matter how far ahead in your input stream is required to look to disambiguate something, the GLR algorithm will be able to determine the correct parse, no matter how far away that disambiguator is. And in fact, you can use ambiguous grammars. And the GLR algorithm will give you, rather than a parse tree, a parse forest, essentially all the possible parses, but represented in a compact form, so this doesn't have an exponential explosion. Now, GLR has been around for a while. The first main paper was in 1985, but the Elkhound implementation is novel because it's actually 10 times faster than the other implementations that previously existed. And the main reason for this is because it actually combines GLR and LALR, taking advantage of the fact that for most programming language grammars, the majority of the input can be parsed using the LALR algorithm. And since this is a much faster algorithm, we can use this as long as we can, and then when the ambiguities arise, actually switch to the more complicated algorithm. And so it seamlessly switches back and forth between these two and is able to therefore be competitive with Bison in terms of like a conventional LAR implementation in terms of performance. Furthermore, unlike previous GLR implementations, you can use arbitrary reduction actions. Most GLR implementations build a parse tree first and then give you that and you can work on it, but a parse tree is very large. So instead, Elkhound uses just user-defined reduction actions that are executed on the fly during parsing rather than actually materializing a parse tree. So just in case you're not that familiar with these technologies, what's the issue with LALR? Well, the problem basically is that it has to decide what the proper interpretation of a token is with just one symbol of look ahead. So I've given a little grammar here. The language only has 3 input strings. There's ABC, EBD, or ABD. But the trouble is that you can't tell whether a leading A should be regarded as the beginning of ABC or the beginning of ABD, because you can't see past that first B symbol. You only have one symbol of look ahead. And so there are 2 possible ways in which an LALR parser could handle this. It could regard it as the beginning of ABC and shift the B, in which case then it could shift the C and finally reduce to an S. Or it could first reduce the A to an E, and then having decided that that's the proper interpretation, go on to shift the B, and then what would then hopefully be a D, and finally reduce that to an S. So the trouble is that we're forced to make decisions too early in LALR. So what GLR will do is it'll extend the traditional LALR parse stack with a structure called the graph structured stack that lets you actually encode multiple potential parse stacks simultaneously. So here along the bottom, I've shown what an LALR parser essentially might be doing with some sort of arithmetic input. But what GLR will do is it'll add additional possible stacks. So this this graph structure here is representing 3 different possible parse stacks. And so basically all the possible configurations of an LALR parser are represented simultaneously. These configurations are kept in sync each time you shift a token. And anytime one of them fails to be able to make progress, you just get rid of it and keep going with the ones you have. So this lets us essentially make the stack non-deterministic. We just keep track of all the possibilities going forward. Now the novel part for Elkhound is being able to switch back and forth between LR and GLR. Basically, LR would be any place where you have sort of a linear structure in your stack, because that's what an LR parser would look like. But if you have some more complicated area in your parse stack, then that's where you're going to have to use the GLR algorithm. And so the thing you need to be able to do is, looking at the top of the stack, decide whether the next action to take, if you know that there's only one possible action, whether that can be executed with the LR algorithm or the GLR algorithm. And this is fairly simple to do. We basically just annotate each node in the parse stack with information about how deep you can go before hitting either a split or the end of the stack. And so then the way this is used is, if you're ready to do a reduction, then you look to see, is the right-hand side of that reduction less than the height of the determinism that you have on your stack. So if you're going to reduce like a 1-symbol right-hand side, then you can use LR. But if you're going to reduce a 3-symbol right-hand side, then you're going to get into the bubble here, and so you have to use the GLR algorithm. Now, it would be easy to make the hybrid be of the form, anytime that stack is entirely linear, use LR, otherwise use GLR. So why do we go to the extra effort of being able to parse despite sort of this bubble here? The reason is you have languages like C++, for example, where you have a rule for a constructor and a rule for a function call. And it's not obvious to the parser which one you're looking at, because you could have like A:B:C, and there are different ways of parsing which is the return type or what's the qualifier and so forth. So with C++, you can get situations where the beginning of your function is still ambiguous. You still don't know what the beginning of the function is supposed to be, and you may never know. But the body of the function you may find is completely easy to parse. And so you want to be able to parse the body of the function quickly despite sort of a latent ambiguity. And so that's what Elkhound's able to do. It's able to use LR whenever possible and then switch to GLR when necessary. The parse actions that you would write are, conceptually anyway, like they would be in Bison. You have a right-hand side. This is a production here. Expr is expr plus expr. The right-hand side has its non-terminals labeled, and then you can just write some C++ code that will be executed whenever that reduction is fired. It'll yield a new semantic value. And so as we fire reductions, we build the parse tree, or the abstract syntax tree is what this would be, bottom up. So as you do this, though, if you encounter an ambiguity, if the grammar is actually ambiguous, there's multiple ways of parsing some fragment, then you'll have 2 possible semantic values for the same sequence of tokens. And so these will be passed to a merge function. That's something the user writes and is just passed in both of the possible interpretations and asked to return a new interpretation for that fragment. It could simply choose one and discard the other, or it could actually construct an explicit representation of ambiguity, which is what's done in the Elsa parser in some places. The point is it's up to the user to decide what to do when you actually encounter the ambiguity. If your grammar is unambiguous, merge will never be called. So this is only if you actually have an ambiguity somewhere in the grammar. Also, because we have sort of potential parsers that may go for a while and then die, but other arms of the parse continue, we may need to deal with memory management depending on exactly what these actions are doing. So there's additional functions dupe and del associated with non-terminals. They're called when a semantic value is used a second time and when it is ultimately not going to be used again. So if, for example, you have an abstract syntax tree with reference counting, you can increment and decrement the reference count using dupe and del. Of course, you can also just leave them as no ops and use a garbage collector or something like that. Okay, so now sort of transitioning into talking about parsing C++, I have a couple examples of things in the C++ language that are difficult to parse, especially in an LALR framework, and how we can actually use GLR to make them easier. So here I've shown the same sequence of tokens that actually has two naive interpretations in C++ because of the overloaded use of this angle bracket. It could either end the type argument to a template, or it could simply be a greater than, and then since plus conveniently can be either unary or binary, we can actually come up with two completely coherent parses of this thing. So if you crack open the C++ standard, you'll find buried somewhere in chapter 14 a little sentence that says, if you see an unparenthesized, that is not inside a parenthesized expression, greater than symbol as the argument to a type, argument to a template, then that's not okay. All right, so the intent of the standard is that you essentially terminate the argument as soon as you can, so you don't think of unparenthesized greater thans as being the greater than operator. But this is not easy to do within an LR framework. In fact, in GCC, which used an LR parser up until version 3.3, they just implemented this wrong. They used sort of a hack with precedence that worked most of the time, but there's plenty of inputs you could give it that it would misparse because they weren't doing what they needed to because it was too difficult. But in a GLR framework, it's actually really easy because we'll just go ahead and parse them both. We'll come up with a tree that actually just has an explicit representation of this ambiguity, and then it's easy, once we get to the merge function, to just go ahead and search through the tree for this exact rule. Just any place you see an argument to a template and then you see a greater than, you just discard that tree. So we can implement this rule within the merge function of the parser once we get both trees, rather than having to just make the decision as soon as you see the token. As an even more difficult example, you're probably familiar with the fact that in C and C++ you have this cast notation, which you just parenthesize a type, and that means to cast. But as usual, we've got conflicts between binary and unary operators. So this fragment here could either be a cast of the address of something, or it could be a bitwise operator, bitwise and. So this exists in C, and the way the decision is supposed to be made is that if A currently looks up in this scope to the name of a type, then this is regarded as a cast, otherwise it's a bitwise and. The usual solution in C is to do what's called the lexer hack, meaning as the lexer is lexing its tokens, it actually consults the symbol table to find out what the current scope maps a name to. However, in C++, this is especially difficult because of the scoping rules. So within the body of a method inside of a class, all of the declarations in that class are visible, meaning that in this example here, this is actually a cast because what's visible is the type def that actually occurs syntactically after it. So to implement the lexer hack for C++, you have to essentially save as unparsed token streams all the method bodies in the class, process all the declarations, then go back and restart the parser on each one of those just so that you can figure out what's a type and what's a name. But again, in the GLR framework, this is actually easy to handle. We'll simply, is that what this next slide is? Sort of. We can simply parse it both ways, and then this method body will contain within it somewhere an ambiguity. But that's fine, we've now parsed it. Later, when the type checker runs, it's easy, because you're now looking at abstract syntax, to just visit all the declarations, ignoring the bodies, build up a symbol table, now go back and reparse the bodies, and you've got all the information you need. So the idea here is that because GLR can have an explicit representation of ambiguity, parsed with ambiguous grammars, we can delay disambiguation until it's most convenient. We're not forced to kind of bind everything together just because the parser has certain needs. We just wait until we have all the information, then make the decision. So this next slide is sort of illustrating exactly how that actually happens, having already parsed the input with two productions. One type name can be identifier, or variable name can be identifier. When we get to the type checker, if we have an expression with two possible interpretations, this is the usual ambiguity resolution rule. You can do other things, but the usual way of handling this is that you just type check them both naively, and hopefully exactly one of them will fail, and you just retain the one that didn't fail. And this is actually what Elsa does in most places to parse C++. There are a few cases where it actually does something different, but this is mainly for performance. Okay. This slide is a little bit out of order, but okay. So the features of Elkhound, the parser generator, were that its performance is within a few percent of Bison if you give it LALR inputs. It does not build a parse tree because the user can do whatever they want with their actions. And it actually allows you to generate parsers in several languages. The main one I use, of course, is generating parsers in C++. But Wes Weimer, another grad student, insisted, he's got to write stuff in OCaml, so went ahead and hacked in an OCaml backend, and then somebody's working on a C# backend. So it can generate parsers in a number of languages. Okay, so now we're talking about, okay. So the Elsa parser, as I illustrated before, it's the main way it handles parsing is using GLR, but it actually has a number of other features that make it extensible. It handles a number of different dialects, ANSI, C++ with GNU extensions, but then even including things like KNRC, and it does this by actually using its own extension mechanisms. So there's a base description that is ANSI, C++, and then extensions for each of the dialects that it knows how to parse. And it does this through extensible components throughout the tool chain, from the lexer all the way through the type checker. Okay, so the Elsa parser is sort of a classic flow. We start with the preprocessed source, parse that lex that into a token stream. The parser generates possibly ambiguous AST. The type checker then resolves the ambiguities and also annotates things like the computed types of expressions, and then some post-processing can be done. Crucially, there's no lexer feedback hack. All the information flows strictly from left to right. So the lexer is just a straightforward flex lexer. This is just written, you're probably very familiar with this. You just have a notation for writing a regular expression and then classify the tokens accordingly. The parser is based on Elkhound. Its merge resolves ambiguities in some cases directly during parsing, like with the unparenthesized angle bracket thing, and otherwise it waits until type checking. As an example of what the parser specification might look like, this is for handling the angle bracket. We have here a non-terminal. In blue are keywords in the Elkhound input language. So I'm defining a non-terminal called template argument. Its semantic value type, actually I have little things that help out here. Semantic value type is template argument star. So we're just declaring the type of the semantic value yielded by these actions. It has productions, so a template argument can either be the name of a type or it can be an expression. Because that is ambiguous, sometimes this merge function will be called. And what this is doing is it's building an explicit representation of the ambiguity. Right. Why does it do that? Yeah. Oh, okay, so there's something confusing about my slide, but the way it's supposed to be handling the ambiguity here, in fact, with angle bracket, is that when it parses something as an assignment expression, it then goes and checks the produced tree to find out whether it actually has an unparenthesized greater than. If so, it'll cancel that action, and then that's the way this. So every time one of these fires, we then pass it through this additional keep function, which lets us filter out things that we actually don't want to keep. So now I don't know why the ambiguity is being kept. Maybe that was just an example. This is a way you could retain the ambiguity later as you connect them together into your abstract syntax. I'll show how that works on another slide. So, but the point is this looks something like Bison input, but with a few extra things like this merge resolution. The abstract syntax is defined using a custom language that looks vaguely similar. This specification is processed by a separate tool to produce C++ classes that implement the abstract syntax. We have names for essentially superclasses, like all the kinds of statement nodes. Then there are specific kinds of statements that are listed. These are implemented as subclasses, C++ subclasses. Associated with each node of the abstract syntax, you can have various kinds of data. So here, every statement has a location. And so this superclass parameter means that every time you construct a statement, you'll have to provide a location. It's a constructor parameter. We also have constructor parameters that are specific to specific subclasses. So for example, if I want to construct a while statement, I say new s while. I first pass a location and then pass these other things. And so those are then all collected together into a single abstract syntax node. We We can also have lists, and you can have fields that are not initialized. This is one extension beyond OCaml. This is so far a lot like the union types in OCaml, but here we have a field, a data field that's mutable and doesn't have to be set when you first construct this thing. You can also, since these are also generating C++ classes, you can actually have methods within them as well. So then after parsing all this ambiguous abstract syntax is handled to the type checker, which is just a big piece of C++ code. It has 5 main jobs. It has to disambiguate the AST, has to compute type annotations, look up symbols, resolve use of overloaded names. It actually does a bit of normalization, inserting some implicit conversions. Those are visible to later analyses, and it also will instantiate templates. This is a necessary part for parsing C++ code, because anytime you refer to a class-valued template ID, you have to then look inside of it to find out what the names of various symbols are, or the types of the symbols inside of it. Yeah?
You said that you don't build an AST, but it looks like you are building an AST.
So what I said is we don't build a parse tree. Right, so we don't have, there's not an explicit one-to-one correspondence between the grammar and the syntax that's generated, but there is between the abstract syntax and the resulting. And there's a factor of 10 difference in size. That's why it's important. If you actually build a parse tree, you have major problems with locality. So abstract syntax is okay, I claim. Okay, and so how does the disambiguation actually work? This is the actual runtime representation of ambiguity that we use. So here I have a program fragment, return paren x paren y. This could again either be a cast or in this case a function call. And so the return has a pointer to the expression that's being returned. It's pointing to the eCast interpretation, but that has then a pointer to the fun call interpretation. And then so this is actually forming a linked list. No other interpretations here. And so then within the cast, of course, we've got the various internal structure there, but then they both share the same representation of x and y. And this is the sharing that lets us actually represent the whole set, the entire parse forest compactly, because we're actually sharing commonly interpreted subtrees. So then the type checker simply has to take this, figure out which one to keep. If it wants to keep the cast, then it'll just break the ambiguity link. If it wants to keep the function call, it'll switch the S return pointer over to the function call. And then when it's done, of course, you'll have just a simple tree structure. The main things Elsa does after the type checker is complete, it can compute a control flow graph. This is just intra-procedural, fairly straightforward. It can check over the abstract syntax to verify invariance. It will do some additional, we call lowering. These are translating C++ constructs that are implicit, like constructor and destructor calls, into explicit function calls to make it easier for program analyses. And you can print it back out as C++ if you like. Now the extension mechanisms, which is sort of the point, come in, I'll show us sort of at each stage. This lets you add new forms to your language. I used the Elsa parser in my PhD research to build a program verifier. And what I was doing there was adding annotations to the language. And so I wanted to add new syntactic constructs that would then be parsed and type checked as the same as the other things. So I used this mechanism for that. So you can add new forms, add new abstract syntax, add methods to type check them. And the goal is to do all this without just directly hacking on the artifact you started with, so that you can continue to share that with other people or with other extensions. So the lexical extension is actually very straightforward. Since this was just a flex lexer, we just syntactically jam the extension into the new lexer description. And so the new token definitions will take precedence over anything that comes after, but now you've got a new flex description that recognizes the combined language. The syntactic extensions are merged by the Elkhound tool itself. If I have these two files, this is the base description for the ANSI C++, and then here's one for GNU, which has the question colon operator, the binary form of that. These are then just union together, so the effective conditional exp non-term simply has all three of these productions together, and we'll just parse using all three of them. The abstract syntax is extended in basically the same way. The tool that reads this knows how to combine these. So here I've got the GNU statement function, a function nested inside of another function, just as another possible piece of abstract syntax. another alternative for a statement. And then finally, when you want to actually type check these, you just just write tcheck functions for them. Tcheck itself was declared as a virtual function on the abstract syntax node, and so then you provide a definition for tcheck for the new nodes, and then the usual C++ virtual dispatch will make sure that everything gets called the way they're supposed to. Okay, so the main features of Elsa, the parser, it has this extensible input language, as I described, handles most of the C++ language. The two things that are just not implemented at all are template parameters. This is passing the name of a template, uninstantiated, as an argument to another template, and the export keyword, which no one understands. Has about 1,000 test files. I claim it's reasonably well documented. And it's actually fairly fast, though the original goal wasn't actually to be all that fast. It's about 30% slower than GCC 2 and much faster than GCC 3. And I have not compared to GCC 4. Okay, so now switching to the third and final part is the program analysis built on top of this. And here I'm mostly presenting other people's work. These are just tools that have been, this is mainly a tool that has been built on top of Elsa. Cqual was a tool to analyze C programs using a qualifier flow paradigm that I'll describe in a moment. Cqual++ is the new version of that built on top of the Elsa front end. The previous version was built on top of a GCC front end. There's a constraint solving backend that Cqual uses called Banshee that I'm not going to talk much about. And what you can do with Cqual specifications is mainly sort of data flow kinds of problems. You can define flow, sources, and sinks, and then see if data from a particular source can reach a particular sink. This can be done to do sort of a tainting analysis. That's kind of the main application, but it was also used to do some stuff for Y2K and a few other more esoteric examples. So the basic idea with this data flow style analysis is that, and this fits in with the notion of extensibility because you're coming in and you're defining what are the flow sources and sinks of interest, is that you have something that's a source, like here the getEnv. And since this is under control of the user, we say it's returning a pointer to something that's tainted. And then we have some other piece of the system that we are going to regard as requiring untainted input, because printf's first argument printf acts like an interpreter. And so if you allow it to take tainted input, then it's going to just run that program effectively. And so what Cqual will do is it will just follow through the program, making sure that everything that's marked tainted then flows to all the places it can go. So the return of getEnv is tainted. This then taints X. This flows into the printf argument, which is now flowing to untainted, and so we detect a bug. And so this is the basic framework in which Cqual operates. You define your sources and sinks and your blockers, and this produces a program analysis. As I just said, the specifications are primarily the sources and sinks. We also need these flow blockers, things that effectively sanitize the input. So if you have something that looks for meta characters in the language that you're passing it to, then that would constitute a blocker. This is mostly work by Jeff Foster, who's at Maryland. So for tainting, typical sources are things that come from the user or the network. Sinks are interpreters like printf system or SQL execute. As I just said, the blockers were things that check for meta characters. Another example of a similar analysis is in Linux. There's this notion of user pointers versus kernel pointers. User pointers come in through a system call, but the user can potentially make them point to various places they shouldn't. And these must first be checked to make sure that they are, in fact, pointing into space that program owns. And at that point, they become sort of fully validated kernel pointers. And so we need to make sure that these aren't being mixed together. We also need to make sure that unchecked user pointers aren't being dereferenced. So the main sources are the system call arguments. The main sink is the deref. And there's various checking functions within Linux that will validate a pointer. And so from Rob Johnson, we have some results of using this to analyze Linux. This found 13 distinct bugs of this kind. Some additional, I guess it was different properties, because that says 17 different security vulnerabilities. This technique found bugs that were missed by manual inspection and other automatic tools. Most of them were exploitable. One sort of interesting side note is that there seemed to be this notion of bug churn, that in fact bugs were being introduced at almost the same rate they were being fixed, which is sort of a funny cultural thing, I guess. As another example, this was actually used to find a Y2K bug in RCS, I think, basically just finding any place where a year variable could flow into something that couldn't represent the full precision. The main features of Cqual++ are that it does interprocedural data flow. It is control flow insensitive. And there's been some work to try to add flow sensitivity, like being able to do protocol checkers like open followed by close. So far, this has been a problem. This has not worked out as well as it could. Jeff has an interesting paper, I forget exactly where it was, maybe a PLDI, where he used the C99 restrict keyword to actually be able to pick out pieces of the program, say that this part doesn't have aliasing problems and that could be automatically checked. And as a result, sort of, so you have an equivalence class of objects in one state. Using restrict, you could pull it out, let it transition through states, and then once it returned back to its nominal state, it could be put back into the collection using the restrict keyword. But this is somebody else's research, and not that familiar with it. Okay, so finally, sort of continuing the theme of extension, I want to sort of mention a product that I've been working on at Coverity, which is a new version of Extend. The Coverity Prevent system looks for bugs in various source code. Extend is a tool that allows users to actually write their own checkers. This one, though it is interrupt procedural, is flow sensitive, and so it is good for doing protocol checking. And we're actually developing a next generation version of this that may be based on the Elsa front end that will allow interprocedural checking, simplify the language somewhat, with the goal actually being that we could actually write specifications for bugs that would be independent of the tool used to analyze them. This would be kind of the goal, really, is to be able to say, okay, here's what it means to have a tainting bug, and then any tool could come along conceivably and use this specification, and then it's just a question of sort of how fast and how thoroughly the tool can execute that spec. So just to wrap up, since again the theme here is extensibility, just want to emphasize that it involves both analysis and language design together, that the language needs to support allowing the user to put in their specific, the properties of interest, and then the tool needs to really work with that. And just to point out one element of that, with Elkhound, it accepts context-free grammars, the whole language of context-free grammars. There's no subset of context-free grammars that's closed under composition besides context-free grammars themselves. So if you want to be able to compose arbitrary extension mechanisms as grammars, it has to accept the full set of context-free grammars. LALR, for example, is not. And so the warm fuzzy closing thing is that I have some hope, sort of believing in static analysis, that at some day it will be as routine for programmers to actually write checkers, static analysis checkers, as it is today that they write test cases. Sort of really trying to push bug finding much closer to when the bugs are actually written. That's it. Some URLs. Yeah.
Yeah, so is Elkhound open source?
Yeah, all of this is open source, available, well, I guess the Coverity is not. But all of these are open source. Elsa and Elkhound are available under a BSD license. Cqual, I think right now, is still GPL, but all of them are available for download at the respective sites on this slide. Yeah.
How much work do you think would be involved in extending Elsa so that it handles all of C++?
Template parameters are fairly easy. A week or two of work, probably. They're not very often used because there's this rebind idiom that actually most people use instead and works without them. Export keyword, well, I don't really understand it very well, so I'm not sure I can even speculate on exactly what's required there. Elsa only tries to be within one translation unit, so it's conceivable that depending on the scope of the project, export actually doesn't matter. But the truth is there are actually some other just kind of bugs. Elsa right now accepts all of Debian, but there are still plenty of examples we have that don't go through Elsa. And so just kind of, say what?
I'm just wondering how much use of C++ there is in Debian.
Well, there's a fair amount. There's KDE, there's Mozilla, there's Qt, stuff like that. And so there are certainly still bugs in Elsa, and it's really hard to speculate on how much effort it takes to get rid of all of them. But typically, if you start with a project that's maybe 1 million lines of code, you can get it to go through Elsa within about a week, something like that. Yeah.
So how good are the error messages? A lot of parsers are sort of notoriously opaque.
The parsing error messages are pretty bad. Elkhound, when it encounters, basically when all the parsers die, Elkhound just aborts. It tells you essentially what it was expecting, but otherwise it bails. So that's not very friendly. I had thought for a long time, I mean for years now, to go ahead and add an error recovery algorithm that Burke and Fisher proposed many years ago, but I never got around to that. So the parsing error messages are actually pretty bad. But if you get through the parser, the type checking error messages are actually quite good because it has all the possible interpretations. So one place where this comes up is that a lot of C++ programmers are not very familiar with how to use the type name keyword. And so if it's missing, for example, GCC will give you just an undecipherable message. But Elkhound will just tell you right here, you should have or should not have used type name because it's able to see the whole thing. And in almost all cases, it knows which part you meant. And it can just, and type name to Elkhound is just a check it does after the fact. It doesn't actually use it for disambiguation. So for some things, it's actually very good. But up until the parser, the error messages are poor. Yeah.
So, Mussel's book on STL has some examples, and I found really hard to compile them in any compiler.
I would not be surprised that there's a lot of crazy stuff you can do with templates. In principle, all the basic functionality is there, like you can write the program that will compute all the primes. That works in Elsa. But there are lots of the name lookup rules for templates, especially with the two-phase lookup and what some compilers implement versus other compilers implement, are awfully difficult to get right. And I still don't thoroughly understand them. So I would not be surprised at all to find that there are textbook examples that don't work. But like I say, typically given a particular example, it doesn't take that much work to actually fix whatever problem may be there. But I certainly couldn't make any promises about. I don't. So what was the name of the book?
Musser, David Musser.
Musser?
STL.
I see. I have not. No. Okay, I'll try. Yes. Okay. Okay. Yeah.
What is the not free software add?
Say that again.
What would be the advantage of using the not free software?
What's the advantage of using the not coverity? Well, it's yes. So why use coverity when all this other stuff is free? Well, the main advantages of the coverity engine actually are the scalability of the interprocedural analysis. What Cqual will do flow properties in a reasonably scalable way, but it can't do flow-sensitive protocol checking in an effective way at this point, and it's unclear when that will happen. So the thing that coverity does very well is finding cases where you have protocol violations that cross procedure boundaries. So use after free, memory leak, various kinds of locking bugs. These are the things that are sort of the bread and butter for coverity. And so it's their analysis that does the interprocedural protocol checking. That's the main strength of coverity stuff. Yeah.
So we use different types of interprocedural stuff here. We use a lot of closures, and so the traditional interprocedural analysis kind of breaks because you pass these function declared and they get executed something later.
Right.
With these different parameters. So are there plans to address that sort of thing?
So the question has to do with the use of closures and interprocedural analysis. Closures are not on the top of the list of things to deal with interprocedurally, at coverity at least. I think it's probably not infeasible, but it's just not a priority right now. The usual approach with coverity essentially is to find what's common and try to adapt the analysis to do that. It's always sort of a race to figure out what are the idioms that the programmers are actually using and how best can we understand them. And since it's sort of the luck of the draw of having chosen a technique that's not common, it's difficult to write program analysis to deal with closures, and as long as no one else is doing it very much, then it's unlikely coverity will either.
Well, it's not impossible to deal with it.
No, I agree. It's not impossible at all. It's just it's cost benefit. Do you spend time improving the analysis for closures, or do you spend time, adding another kind of protocol? Or
So you said that you're going to be working on a new language to define these checkers.
yes.
But I would assume that that language would preclude the ability to extend it to closures. Whereas if you had direct access to the covariant machine, you would be able to implement this.
So the question has to do with the new version of extend handling closures. I would say that the idea is not sufficiently baked yet that I could actually say it precludes closures, but it is not on the radar of things to actually go for. What you say is quite plausible, that in fact it will not provide sufficient functionality to deal with closures, and that if you had more direct access to the covariant engine, it could. Having brought it up, I'll think about what it would take to make that possible, but like I say, it's not likely to be the high priority item. Any other questions? Okay, thank you.